Hi, I'm Stefan, and I'm the host and organizer of the emBO++, the next level conference for embedded software developers. The talk you're about to see is about unsupervised federated learning for microphone clusters in acoustic sensor networks. It was given by René Glitza at the emBO 2021, and thanks to Leica Geosystems, you can check this video out for free.
Okay, hello everyone. I'm René Glitza and welcome to my presentation about unsupervised federated learning for the estimation of microphone clusters in acoustic sensor networks. I will present you today the research in this field I have done, and then let's just dive into it. So first I will give you a short introduction into the topic with the motivation and the idea we had, what this actually is. And then I will give some brief explanation about room acoustics and artificial neural networks to understand a bit more what federated learning is and how it works. This is then followed with the main algorithm of our research, unsupervised clustered federated learning. And then I will give you some examples of clustering experiments and gender recognition experiments, which we did with simulations to prove the performance of this algorithm. In the end, I will give some short conclusion with an outlook. So who am I? My name is René Glitzer and I'm lead engineer in systems design at Auto Intern here in Bochum. And I'm also part-time research assistant at the Institute of Communication Acoustics at the Ruhr University Bochum. I have a master's in electrical and information engineering, where my major was embedded systems, but I mainly focused on audio signal processing and artificial neural networks. Also, I was the former president of a local VDE Youngnet group here in Bochum, which is called Hochschulgruppe Bochum. And now let's go into the topic. Um, Countless applications in our daily lives use audio signal processing. And because of the decreasing costs in acoustic sensors and also more powerful processors, the trend goes towards multi-channel signal processing. And if you have multiple microphones in an array, those are usually in a single geometric location. You have an example from the SINS apartment, which is a holiday apartment from the SINS database, where you have multiple microphone arrays in this apartment. Now just consider you have one of those microphone arrays, which consist of maybe 3 or 4 microphones and a sound source anywhere in this apartment. Because the probability of this microphone array here being close to the source is pretty low, you could end up having a very low signal to noise ratio so that you can't really separate the signal from some noise. Also, because you have a single location, devices that use those microphones are also limited by the power, which are also often IoT devices or smartphones which are wirelessly connected. So that's why acoustic sensor networks come in handy. So acoustic sensor networks are randomly distributed, often wireless microphone nodes in an environment, like you can see here on the right. All those red ones here are microphone nodes. And now the probability of a target being close to the source is way higher. Like it can go anywhere here in this apartment, and I'm close to a source. And applications that use acoustic sensor networks are, for instance, smart homes, ambient assisted living, also machine fault diagnosis, or even surveillance. But there's a problem with acoustic sensor networks. In most cases, you don't know the position of those microphones beforehand. Like a picture in here is often generated afterwards. And also the data synchronization between the nodes to have like the same data at a server is quite difficult. Often they use wireless communication, so you have some delay with, for instance, Bluetooth or Wi-Fi. And the clocks can also be asynchronous. So featuring together those signals might be difficult. So acoustic sensor network can be enhanced by providing additional information about the position. And this has been shown for the estimation of source dominant microphone clusters in 2 examples, for instance. So source dominant means that you have some sound source in a room, which is dominant for some microphones that are close. And it has shown to improve acoustic sensor network-based signal classification, so to classify what signal you have there. and also source separation performance, so to separate two or more sources from each other. But these approaches use some feature representation of raw audio. That means some transformation of the audio signal that's been recorded. And because acoustic sensor networks are also often in unsafe and often wireless communication environments, you don't want to send any raw audio, but you rather desire for an approach like privacy by design. For instance, in the European Union Data General Protection Regulation. So how do we estimate those clusters without actually sending recorded data is the question now. Well, and we had the idea, why not share locally your network parameters to get groups of microphones around sources? This would make it very difficult to reconstruct the data on the other hand, because no part of this of those features or the recorded data is sent to a server at any time. And there are actually algorithms that use that share locally your network parameters, and they are federated learning. Federated learning is machine learning algorithms that use supervised learning applications. So supervised means they have some labels to their data, which are normally generated by some user interaction with the local device. Imagine you have a smartphone that trains a network on your computer, and the interface is you typing or swiping or looking at something. This would be a label that you can use. And this federated learning was first proposed by Google. And then clustered federated came up and extended federated learning by grouping devices with similar behavior in the data with each other to increase the performance across all devices even further. So we have an algorithm that can already get you clusters from those neural network parameters. But let's go further. How can we obtain those relationship informations with acoustic sensor network space with privacy? So we want to have microphone clusters. So that can help us to improve the algorithms that use acoustic sensor network space applications. And in acoustic sensor networks, we don't have only very short audio segments we can deal with. For instance, only a few seconds. And we only have the raw audio, so no training labels, only what's recorded by the microphone, no position, nothing else. So we need to extend this clustered federated learning, which was only used for a supervised learning application, to an unsupervised fashion to get those clustering informations. And we test this with multiple different sound sources in an enclosed room, like shown here on the right, which is a simulation scenario which we used from the room I've shown you before. So this is actually a two-dimensional picture of the simulation room we used, where we have those four sources here, and the red crosses are all microphones. So how do we estimate the clusters from neural network weight updates and from unsupervised training? Is the question that I would like to answer you throughout this presentation. But before I do this directly, I will explain a bit about room acoustics so you might understand how this, why this can actually work. So in room acoustics, or in any room actually in the reality, you have some sound sources and some receivers. So sound source might be someone speaking or your loudspeaker playing music, and the receiver might be you just listening to it. And the room where you're in changes the sound as it is emitted by the source on the way to you when it receives you. And how this change, how this change is described by the room impulse response. And this room impulse response consists of multiple arrivals of the sound. And the first arrival is the direct sound. So the direct sound is the sound that travels directly from a sound source to your ear. And because it's directly, it has the lowest delay, so it arrives the earliest, and has the highest amplitude, so the most energy. Then you have some early reflections. Those bounce just a few times from walls. Because they bounce and reflect here from walls, the path is longer, so you also have a longer delay, as you only travel with the speed of sound. And because it reflects, you also have less energy. And you have more than just one reflection. You have as many reflections as the sound can hit. And if you can separate them, you call them reflections. And if you can't separate them by the naked eye anymore, you're talking about the reverb. And this goes on almost infinitely. So I have one simulation scenario to show you, which I did in CAD Acoustics. That's an acoustic simulation software. And I have here a shoebox shaped room like shown here with one receiver and two active sources. You can see here the direct sound path of those two sources to the receiver. And down here, you can see the impulses you have that arrive where the sound arrives. And the one from A0 arrives the first and has the higher energy as the one from A1, which has lower energy and arrives later. So now let's have a look at the first order reflections. So reflections that are only once reflected by the walls. You can see that here from the source A0, you have reflections that arrive even earlier than the direct sound from the source A1 here, and even more. And if you go now to the second order, you see there are way more reflections. And if you have a look at the third order, that's already too much to see. And for normal simulation to be accurate enough, you need about an order of 15 or 20. So the key, what you should remember from this is, if you have two sources that are active simultaneously, one is probably louder and arrives earlier than the sound of the other, which is quieter. So keep this in mind. That might be useful for the understanding. Now, let's go to the basics of artificial neural networks. So you probably all have heard the phrase artificial intelligence, or short AI. And the goal of so the challenge from AI is problems that are easy to understand and perform for humans are hard to describe for them formally. So have in mind you have like recognizing spoken words, like you do it right now with my presentation here. For you, it's an easy task, but how do you describe like how this would perform? Like, do you know some mathematical equation or algorithm that can do precisely this? And because this is kind of hard, we use artificial intelligence to gather the knowledge of recognizing those spoken words from the experience it gains when training on it. And humans do not specify those knowledge of this artificial intelligence. And AI is like the basic word for algorithms. And it's a technique that enables machines to solve a task in a way like humans would do. And machine learning is a subset of artificial intelligence. And those are algorithms that allow computers to learn from examples without being explicitly programmed. So they're a bit more intelligent. And artificial neural networks are brain-inspired learning models. So they are kind of like the neurons in your brain, but in a mathematical way. And deep learning are artificial neural networks that are deeper, like with more neurons and also multi-dimensional inputs. But this goes a little bit too high for this presentation here. So let's focus on artificial neural networks. Artificial neural networks learn complicated concepts by building them out of simpler ones. And those simpler ones are, for instance, the artificial neurons, which are the elementary units of artificial neural networks. And they're inspired by the biological neurons you have in your brain, where you have inputs here, which are weighted through some weighting, and then summed up in a transfer function over here. So you have a summed input from all your net input that is weighted by the inputs here. So this net input here goes into an activation function. And if the input is higher than a certain threshold, you get an activation, so a signal that's sent up to the next neuron. This is also how your brain works. And by connecting them in a way, you can get more complicated structures out of it. And here I have a feed-forward network, which is one of the very basic artificial neural networks, where you have three input nodes. Those input nodes are connected with those weightings to to some other nodes here in the hidden layer, for instance. The hidden layer is called hidden because you normally don't see it from the outside and don't know what happens in here. And then these hidden layer neurons are also connected then to the output neurons where you see then your result. So you can kind of imagine this as a black box where what happens in here you don't know and is changed by the way you train it. Here is a picture of some of one layer where you have here the inputs and the weight that goes to the inputs with some bias. And these weights are changed when training. So when you tell the network how to get the most performance, those weights are changed. And this is what you also should keep in mind, that a neural network is trained by changing the weights inside this network to perform the task you want it to do. So what's the difference between supervised learning and unsupervised learning? In supervised learning, you pair an input with a desired output. Let's go for an example on pattern recognition, which is often called classification. And in image classification, you might have a picture of a cat. And you give this picture into a network and also a label, which is cat. So then your network knows, okay, this is a picture of a cat, and you give them multiple or thousands, maybe million picture of cats, or in which are all different, and it learns how to recognize a cat. Same applies for speech recognition. Regression is another example for supervised learning, which is also often called approximation, where you can perform predictions or forecasting, like weather forecasting or stock predictions, or also have like causal relationships between variables, often used in physics. Unsupervised learning works a bit differently than supervised learning. Here you don't have any desired output, you only have the input data. So only the data you gain and a cost function which you model by yourself. So you know your problem and you can describe a cost function. And one of the most common cost functions is one for compression, which is called the mean squared error. So in compression, you want the output signal here, y hat, to be close to the input signal y. So you subtract them, square them, and perform an average, and try to reduce this error here throughout the training. So unsupervised learning is often used for estimation problems like clustering, which is exactly what we want to do here. So grouping together things that are similar. Compression, so data compression, which is dependent on your data you actually have, or the estimation of statistical distributions and filtering. So an autoencoder is one of the most common unsupervised models, and it's used for dimension reduction, so compression of data. And it consists basically of three types. One is an encoder, where you give in some input data here, which is then reduced until a bottleneck. What's here you have in signals in the bottleneck can be sent over some communication channel, for instance, a wireless channel. And then on the other side, you have a decoder, which is kind of the opposite of the encoder, so the inverse, which reconstructs those features you had here in the bottleneck to something that looks similar like your input. So this model you want to train to for the reconstruction to be as close as possible to the original. And I have here one example of a very, very simple autoencoder with only two bottleneck nodes, like two of those artificial neurons in the middle, which tries to reconstruct pictures of 20 times 20 pixels from the MNIST dataset, so some fashion ones. And you can see here that the reconstruction has some blurry images, but they're kind of show what actually was before. So with compression, if it's not a lossless compression, you have some error in this. And because we have audio signals, we need to pre-process them before putting them into a neural network. And for audio signal processing, this is one of the most often used ones to perform feature extraction. That's called this pre-processing of your data. And when you record audio, you have an audio signal in time, which is a stream. So one stream. And then you chunk the stream down into separate, smaller parts of audio. And then you take those parts of audio and transform them with a discrete Fourier transformation into a frequency domain. So now you know which frequencies are how loud. You might have seen them with an equalizer somewhere in with audio. And then what we also do is we filter them with a MEL filter bank. MEL filter bank tries to filter the frequencies kind of like your human ear does, because you don't hear all frequencies exactly the same linear way as they are in reality. You have some better resolution at the lower frequencies and some worse resolution at the high frequencies. And also, we perform a logarithmic function on this. So maybe you've heard the word decibel before. So the energy of the sound is not like not linear when you perceive it with your ear. So 6 decibel more in your ear is only slightly louder, but it is the double of the power you need to produce the signal. So so to conclude this here, you have an audio signal that's in the time domain, and in the end, you get pictures like shown here on the right. So now let's go into how federated learning works. Federated learning is the distributed learning of neural network parameters, so where the clients can train on their own local data sets. So you have embedded devices, and they all can train on some data they have locally. And then they exchange those weight updates with the global server, which averages them and distributes them to the clients again. With this approach, you don't share any of the data, which makes it privacy aware, which is a pretty cool feature if you don't want to involve any um, uh, like if you don't want to send any data from your customers to a server, which can be intercepted. So, and it can be described like in a 3-step iterative process over some communication rounds, as they are called. And in the first step, you have the clients that synchronize with the server. So the clients download the weights over here so they all have the same weights. And the next step, all clients train on their own data to improve their own model. And then they upload those weights to the server, which averages those weights and gets a new model, which is then distributed in the next communication round. So this way you can use smartphones for training huge neural network weights, and maybe also Alexas or whatever you just have laying around that has a connection to a server and data. So, but there's also a problem with federated learning. And this one parameter configuration that you have might not fit all clients best. So the data here in your clients might be different from each other. So you have incongruent data distributions, but you want to separate into clusters of clients that have similar ones. So this would be the idea to separate those clients that are similar, and they train then one virtual server. So only one server that belongs to the clients that are similar. And how do we find those clusters? This is where federated learning comes into play. And federated learning uses approach is to cluster clients with similar data, so concurrent data distributions, and it uses the cosine similarities between the node weight update vectors. This sounds a bit complicated, but it's actually easy to understand. Just imagine your weights as a vector which points in some direction. And if this vector of one client and another client points in the same direction, then you want to group them together. But if they point in an opposite direction, then you don't want to point them together. So it's kind of like the angle between the two vectors. And if you compute this from all clients you have to all other clients, then you get a symmetrical matrix like shown here on the right, which is called the cosine similarity matrix. This is one from one of my simulations here. And on this, you perform B-partitioning, so which is a clustering algorithm that groups together clients here which have a higher similarity. And you can already see by the shades of the squares here that some clients are similar to each other, but some are not similar. So the white ones here are not similar, the blue ones here are similar. And you separate it in them into two clusters as long as there's some stopping. So you get a hierarchical clustering that gets finer and finer. And when should you perform this clustering? So if the server reaches a stationary solution, so you have this global model that can't improve that much anymore. This is usually shown with the mean weight updates. So the average of all weight updates between the clients is reaching a saturation. So it's getting very low. But you have some clients that still have a high variation in those weight updates. So this normally means that they still have room to improve. So if this happens, if they're above and below a certain threshold, then you perform this B-partitioning. And you can see that now the distance between the mean and the max here is way closer than before. So let's go into unsupervised clustered federated learning, finally, the algorithm we were working on. And to recap this, federated learning and clustered federated learning aims for good performance on the network. So they want to train a neural network that gets the best accuracy for all clients, and they use labeled data. In unsupervised clustered federated learning, so our algorithm, we actually don't care about the performance of this network. We only care about the clusters we get from it. So we want to obtain some information about those clusters that help to enhance acoustic sensor network-based applications and do not need any labeled data. And so why do we think this actually works? If we consider a room with multiple different sound sources here, like we have one sound source here in the living room, another one here in the kitchen, then one here in this bathroom, no one here in the toilet or the corridor, and one here in the bathroom. The microphones that are here in this room, they have a different reverberation in the signal. Maybe you remember this impulse response I showed you in the beginning. And they also have a different dominant sound source. So the ones here close to the couch probably have the source A3 as dominant, so as loudest, while the ones in the bedroom have the ones B0 here as loudest. So if we now train an autoencoder, so the neural network that compresses audio signals, we think that if you have similar signals that we train on, the changes in the networks are also similar. And as you will see later, this is actually true. So the algorithm is basically a three-stage approach. First, we need to pre-train the server, so the autoencoder. Then we perform clustered federated learning, so the federated client training with clustering. And in the last step, we do some post-processing, which are cluster membership calculations. So in the first stage, that we pre-train a lightweight autoencoder, so not a very high-level model, to reconstruct log-Melbourne energies of speech, so the features I've shown you before. And after we pre-trained this, we freeze all layers, so the encoder layers and the decoder layers, except the bottleneck. So those weights here in the encoder and decoder can't change anymore. And the ones in the bottleneck, we also reset them. So the weights in here do not contain any information about the previous learning anymore. This has two benefits. One, it's easier to learn on lesser data. In acoustic sensor networks, we have only a few seconds of data. And the other one is that we have to transmit fewer parameters because the encoder and decoder can change. Only the bottleneck and those weights here are actually the lowest ones you have. So now the clients only need to update the bottleneck layer. And they do this in the second stage, so the clustered federated learning iteration loop. So there, the clients train on their own microphone recordings. They check if the threshold is reached for performing the clustering, so the grouping to two partitions. If so, they compute this cosine similarity and perform the bipartitioning. And in the end of this loop, they update their own virtual server so that they stay synchronous with each other. So let's go and have a look at a SHOEBOX room here with two active sound sources and some microphones randomly positioned in here. Because we have two different sound sources with two different signals, we have a high variation in the data through those microphone nodes. And now we want to group those together. And as a threshold, we use here the ratio between the mean and weight update norm, which is already different than clustered federated learning because it generalizes way better in acoustic scenarios as we have seen in our research. And there's also an automatic stopping criteria. So if there's no splitting after a defined number of rounds, so if this threshold isn't reached for a certain number of rounds, then we can stop this algorithm automatically and get a fixed number of clusters. And so the end result would be a cluster configuration. Here is one with only two clusters for simplicity reasons. And you can see the two sources here. And the red nodes here belong to the source probably on this side and the blue ones on this side. And here, this green circle around it is called the critical distance. Here's the energy of the direct sound from a source equal to the energy of the reverb. So all that comes back from the room. And many nodes are inside this critical distance, but a lot of are outside this critical distance and even between the two nodes. And you might think that these nodes here in the middle might not help to improve those acoustic sensor network-based applications very much. And you're right, because they have a very big signal, they can even lower the performance. So we need to find a way to weight those clients, and we do this by using cluster membership values. And those cluster membership values are also computed using network parameters and not features, so not any signal, and is still privacy aware. And so how do we compute them? We need to find a reference node, so one specific node per cluster. And we can look at this by using the intra-cluster and the cross-cluster similarity. So how similar each client in one cluster is to all the other ones in the same cluster, and how each client is similar to all the other nodes in the opposite cluster. And when adding them together with a weighting factor and taking the minimum, we get a reference node. From there, we can compute the cosine, just take the cosine similarities to those reference nodes, which are, for instance, here this one and this one, and normalize them between 0 and 1. And we got the picture as shown here in figure 23. The reference node always has here a membership value of 1, while the ones inside the critical distance have a high membership value, and the ones outside the critical distance a rather low membership value, probably due to the very mixed signal you have. And the ones here, the outlier, has the lowest. This is a very good example and exactly what we were aiming for. So to recap this, artificial neural networks are trained by changing weight updates, and an autoencoder compresses the input features to reconstruct them. And federated learning algorithms are artificial neural networks that are trained locally and update the weights to a server. And this server contains a global model that's distributed to all the clients that train locally. And cluster federated learning extends federated learning to group clients with similar weights updates together by using the cosine similarity. And in unsupervised clustered federated learning, an autoencoder is pre-trained to reset and then reset the bottleneck layer, and all the other layers are frozen. So only the bottleneck layer weights, so the ones in the middle that are compressed, can change.
Wir sind hier in einem kleineren Grossraumbüro.
Bei der Leitung habe ich die Freiheit, dass ich, wenn ich anfange und wenn ich höre mit dem Arbeiten, eigentlich selber einteilen kann.
Overall, how I will do it, it's just up to me and they give me a lot of freedom.
Für mich ist die Faszination, mit anderen Leuten einen kreativen Moment zu generieren.
Great colleagues, great environment basically.
It's really nice here and I don't have any issues living here.
Am meisten schätze ich in den Like Geosystems, dass wir ein sehr junges Team sind, sowie dass ich auch meine Arbeitszeit in einem gewissen Raum selber bestimmen kann.
And I could merge my life hobby with my office job.
Das Besondere an der Leica Geosystem ist sicher die Kultur und die Dynamik, die es gibt in dem Team. Es ist jeden Tag ein bisschen anders.
We have good organization which will help you to get used to the company in the first couple of months especially.
Das ist sehr interessant und ja, macht mir Spaß.
And the other weights don't change anymore. And cluster federated learning is then used to for training the clients on the recordings. It's checked for the threshold and performs speed partitioning on those same cosine similarities as cluster federated learning does. And in the end, we have some membership value calculations in post-processing. So now let me show you some experiments to actually prove that this also works. So we use some simulation scenarios for this because recording so much data to prove that this algorithm works would take up too much time. So I modeled the SINS apartment from the SINS database of which consists of continuously audio recordings of one person living here in SketchUp. So this model is then exported with a self-written plugin by me for the simulation software Cat Acoustic, which uses cone tracing for simulating those room impulse responses that we can use to change the signals from a different data set. And this different data set is a subset of the LibreC corpus, namely the Trachnine 100, and it contains of 251 gender balanced speakers from audio bit recordings, removed silent parts with voice activity detection, and split the data set into a server and a client set. This splitting is important because in artificial intelligence, you don't want to test your algorithm with the same data you actually trained it on. This would just give you false results because you would think that it behaves good, but it actually just learned the data you had, and it doesn't tell you if it generalizes good on different data that it hasn't seen before. So the clients, the 94 speakers from the client subset were never used for the training of this data set. Then we evaluated it using 3 rooms. One is a shoebox shaped room, and 2 are the SINS apartment, where we use the whole apartment, and also once only the living room. And there we have 2 or 4 simultaneously active sound sources and randomly distributed receivers. So we get 10 room configurations per room. And each room configuration has 20 different gender balanced speaker pairs. So 1 female, 1 male if it's 2, or 2 female, 2 male if there are 4 sources. And we have 40 seconds of speech per speaker to perform this clustering on. So we have in the end 200 simulation scenarios per room that we can use to evaluate this algorithm, which should be enough to say that it actually works. So for the clustering results in the shoebox room, I have here the results with an old threshold, which uses the gradient of the mean weight update norm to be consistent with the paper that we will be soon at the ICAST conference. And to evaluate here, we use a measure that's called normalized cluster to source distance. It again looks a bit complicated, but it's simple to understand. You have a position here of a source. So those are here the source position, and the position, the mean position of a cluster. So the average position of all clients in a cluster, which would be, for instance, here and here. So you take this distance between the two, the source and the average geometrical position of the cluster, and divide it by the distance between the 2 sources here. And so if the value is low to one source and big to the other one, so this distance here is big, this is a good result. So and you can see that here the centroids, as they are called, the average positions, are barely inside this critical distance. But if we apply now the membership value weighting, This gets even closer to the source, with this one being almost at the center here. So it shows that we get closer in this example. And if you have a look at the table, you can see that for all 200 simulation scenarios, we get a very small number of about 0.1 to the closed source and about 0.95, so almost the distance between the two sources to the opposing. So this shows a good result. And now I have here one example from the SINS apartment. So here we have this apartment with the living room, and here's a small kitchen, the bedroom, the toilet, here the corridor, and the bathroom. And you start with all clients or all microphones being in one cluster. And then in the third round here, the clients got split up into the living room and the rest of the rooms automatically. So it detected that those here are different than these ones. And then again, in the fourth round, you see that those microphones over here got also separated from the rest. And the ones here in the bedroom got separated from the toilet, corridor, and the bathroom. But we have an outlier here, but it also was detected as an outlier because it has a very low membership value. So in the next round, you see there was a second cluster that got detected here in the living room. So we have two clusters that are source dominant, so they belong to a source, and one cluster that's here a background cluster of microphones. Over here you have the bedroom, which wasn't separated again. So here, which is nice to see that it detected to not separate those microphones from each other anymore because they are already belonging to each other. And here you can see that the ones in the toilet and the one here in the corridor were split up from the rest over here. This is probably because they have a lower signal than those here. Then in the sixth one, the bathroom was split up from the corridor, and in the seventh one, the corridor was split up into two microphones. This is probably because those here have a higher signal from the one here in the bathroom, and those two here through the door over here from the living room. So to get this into some numbers, we use again the normalized cluster to source distance, but this time we divide it by the average position between the sources because we have more than just two, we have actually four. And then we get for the first four clusters, remember we can have more clusters than we have sources now, the metrics over here. What's important to see is that these numbers here are small and the rest are high. I see some questions already in the chat. I hope it's okay if I answer them at the end. And then if we have a look at the rest of the clusters, you can see already here some triangles here, which because we sorted them by these triangles. So we get some diagonals. So we get microphone clusters which are close to a source, but not as close as the others, which is interesting to see. Also, with the 200 simulation scenarios, we never got more than 11 clusters in this scenario. So it also proves that we can automatically stop our algorithm. Now to some gender recognition experiments, which are a bit more real-world scenarios. For the SHOEBOX room, we use those two clusters we got before, and the label of a cluster is the gender of the source that's dominant in this cluster. And if we only have clusters without membership values, we get an accuracy of detecting the correct speaker gender of 88%. This is not actually a very good result. But if we apply the membership values, we get 94%. And this is a decent result. We can now add another threshold so we can throw away clients that have membership values, for instance, below 0.5, which are here now in white. We get a better result of 97%. We can even make this higher to 0.9, but the accuracy stays the same or even degrades a little bit because we don't have so many clients now in the clusters to average the prediction on. So for the SINS apartment, this is we needed to filter out or sort out some of the clusters. So we only take the ones that are source dominant. We can do this using two different approaches. One is the ones from the matrix I've shown you before, where we take the first four columns, which are closest to the source. But there we need two types of information. One is the correct gender, and to evaluate how good it is, but also we need to know the positions. But with the probability-based selection, so we only need to know the certainty of a gender classifier of a specific gender. So how sure this classifier is that it's a specific gender. And the results with only using clustering without membership values is even lower now with 80%. As you can see, for both approaches, they actually detect the same ones, same clusters. This is probably because we have a more signal mixture than we have before. But if we now apply the membership values, you can see that it goes over 94% in those multi-room scenarios where the cluster to source distance, so the matrix selected one, has a peak at 0.8 for the membership value threshold and 0.5 for the probability one. This is probably because the probability-based approach does not always select the best cluster, but often it does. But if it doesn't, then it's better to average the prediction of the clients, so the microphones. So now I'm at the end of this presentation. I would like to give you a short conclusion. So I proposed an estimation of microphone clusters under privacy constraints, which uses an unsupervised adaptation of clustered federated learning for acoustic sensor networks, which we call unsupervised clustered federated learning. And there we use an autoencoder as a server model, which only has a subset of trainable neural network parameters for the clients, so the microphone nodes. And the cluster estimation is based on neural network weight updates and not feature representation. So we don't send any recorded data to the server at any point. And we have an automatic threshold for performing B-partitioning, so separating clients and microphones into two groups, and also to stop this B-partitioning. And membership values are based on the cosine similarity, so still the weight updates, which are computed in a post-processing. And in the end, we have good clustering performance, which we evaluated using cluster to source distance, and improved gender recognition when applying clustering and membership values. If you're interested to this topic, we have a paper that was accepted by the ICAP conference, so the International Conference on Acoustic Speech and Signal Processing. It's called the Estimation of Microphone Clusters in Acoustic Sensor Networks using Unsupervised Federated Learning. And we also submitted another one for complex multi-source environments for the European Signal Processing Conference. And as an outlook, like some ideas what you can actually do with this. So it was just tested as a proof of concept and it worked, but you can also use, instead of microphones, different sensors. For instance, you can have video streams, pressure sensors, temperature, vibration, or any combination together of those sensors and use it for different applications to get groups with privacy constraints. Also, we haven't actually tested it with real-world recordings now, so we want to do it with the voice data set. And also the test for privacy constraints we need to do. And we can also apply an orthogonal transformation of the weight updates to encrypt those updates even further. So maybe it's even a lower possibility to get any meta information about this of this process. And some use cases we could think of investigating the performance with, for instance, weight work detection. So where you use privacy preserving weight work detection algorithm, for instance, in smart assistants or speaker identification, you could use it for it, or scene analysis. And in the end, I would like to give a special thanks to Alexandru Nelos, who supported me through the collaboration in this research, and Bengt Ine Dalenberg for providing a free version of CAD Acoustic for the research and also supporting me with the acoustic simulations. And this was it from my side. Thank you very much for the attention. And if you have any questions, I would like to ask them now. And after this presentation, I'm also here in the meetup zone, so you can speak with me. Thank you. So I see already 2 questions from Paul in the chat. Wouldn't overfitting by transmitting too often compromise the privacy awareness? So overfitting by transmitting too often compromise the privacy awareness. So the privacy awareness is a bit is not dependent on the overfitting per se. Like you would see maybe the weights are synchronized within the server. And if you have an overfitting, which we actually want to get an overfitting because it shows that we go into some sort of direction. You still have only the weight updates where you can't see, is this now a male speaker, a female speaker, or is this in the living room, in the bedroom, or something else? You might only can intercept that those weights are similar, so you can only get the same information the server does, so to group some signals together. And the next question is, would further features such as signal strength to a router be added directly to the federated training, or would that be more like assisted training? Yeah, signal strength, that's a good point. You could use this as a further input to the network itself. So to train it as a next dimension or give some further information. But what you can also do is you might not only have one router or might not know the position to a router. So if you have multiple routers, so a sensor system of wireless nodes that are communicating over Bluetooth or some other radio transmission, you could actually use this to group them together as well. So it doesn't actually have to be audio signals. You can also use the signal strength there. And is reshuffling the clustering not possible to avoid repair false source categorizing? So if you reshuffle the clustering, there is actually an approach from Sattler where he explained clustered federated learning to go back a step and prove and see if this step you did for the clustering was actually correct. We haven't done this in our research yet, but we have also seen that it works pretty good with our results. So shuffling, from our experience, we try to shuffle each communication route to get clustering results, but it has shown that the changes were not big enough to get consistent results, like stable results in the clustering. Like you get a too high variation if you shuffle this clustering every time. I hope that answers your questions, Paul. Are there any other questions? Okay, I don't see any questions in the chat anymore. So if you would like to meet me and talk in a smaller group, I will be on the left in the meetup zone.
If you found this video informative, make sure to subscribe our channel. Click the thumbs up if you liked it, or leave us a comment on what we could improve. If you are looking for a job in the embedded industry, or you've got one to offer, drop us a mail to jobs@embo.io. That's jobs@embo.io. And we'll make sure that you match up. My name is Stefan Bückelmann, and as long as you keep watching, we'll keep covering the internals of the embedded industry.